Everybody, welcome to week 2 of Geog 473-673. So last week we kind of covered some basic scripts and we went through some carbon dioxide plotting and how to look at that. And then I asked you to kind of run through this CARS quick example, just kind of getting used to how to code and just kind of do some basic things. This week we're really going to be jumping into scientific R scripts. And what I really mean by that is just R coding for a specific scientific purpose. So for this example, we're going to be looking at GOES-16 SST. GOES is a geostationary satellite. It has the highest temporal resolution of any geostationary satellite America has ever seen. And so this was just launched about 2 years ago now, and it offers some amazing data. And one data file that we are going to be taking a look at right here is their sea surface temperature data product. So this offers sea surface temperature for just about the entire Western Hemisphere here. And we are specifically going to take a look at the snapshot of the Atlantic Basin that we are mostly concerned with here at University of Delaware. So we're going to be taking a look at plotting this up and dealing with some data that is NetCDF4. So before we get started, I encouraged everybody to do this earlier, but just in case you haven't, go to the course GitHub page and you'll notice this code button right here. And what you can do here is you can download all of this code as a zip file. After that code is completely downloaded as a zip file, you have every data set and every script that I've written, by the way, all on your local machine. This will really make it easier to jump into the datasets folder and grab what you need. So the datasets folder is where all of the datasets that we'll use for the class live, and this long, ugly naming convention is what we're going to be using here today. So first thing we're going to do after we have all that downloaded is we're going to pop open R. And I'm going to create a new script, and boom, here we go. We got our script ready to go, ready for writing. And now I'm just going to copy all of this over. And I gave you the entire scope of the script first, and then I walked through it step by step. And then we kind of run through an in-class exercise, which I will not be grading, but I just encourage you to run through it and try to get and replicate this image. And then I kind of dive into just quickly, just a little bit extra recap of data types and what those are looking like. So back to this script, okay? So we're going to go ahead and first thing is first, we are going to load in our libraries. Now, a lot of times when you load in libraries, you're going to notice some font or some text that is responsive to just like messages from the loading of the packages. Most of these can be ignored. However, if you do not have either of these installed yet, an error message is going to pop up like, error, this package has not been found. Now, for me, I already have these pre-installed. I use these all the time. So once you install a package once, they're installed on your computer. Barring any major changes you make to your computer, it will be installed for forever. So if you do not have these packages installed, I encourage you to come down here to the console and install that packages, which is the function that we use. It's already pre-built, and install NetCDF4. Now, in my case, what's going on is because I already have this package installed, it's going to say, okay, this package is already installed, we can't install it, but we can update it for you. And then there's a little box that pops up, updating loaded packages, and no, I don't want to update this at all. Sometimes you do want to update, but in this case, there's no major updates that have come out for this package, so I'm just going to refrain from doing so. So after you install these packages, you're going to need to load them in via the library function. And so that just tells R, hey, I want to be able to use any function within this package, NetCDF4 or fields. I want to be able to use any function in there. Now that these are loaded, we can type things like ncvar get Remember, tab is your best friend. And this is a function from the netcdf4 package or library. And this is a super useful function that we'll get into a little bit more, but just as a quick reminder, if I did not load in netcdf4, the ncdf4 package, I would not have been able to use this function. So here we are at line 6 of this script, and what we're doing here, and I'm going to start commenting these lines out. And again, I kind of run through this more in the tutorial as well, but I just wanted to have an audio example for those of you. Is the first thing we're going to do is we're going to load the file. So this is the line that we're going to load the file that we want. The function that we're going to be using here is ncopen. ncopen comes from the ncdf4 package. Notice what I just deleted. I'm going to pop Control Z, put that back. When I query ncdf4 : this is a shortcut around having to load in the library. This is saying, okay, hey R, I'm going to call the ncopen function, and that function is in the ncdf4 library. That's all this is doing. We do not need this. It's sometimes just a good coding practice, and sometimes if you just look at code from other people online, you will see them coding like this. The reason that I am doing this for right now is to show you, for one, it can be done, but for two, to get you familiar with which functions are coming from which packages. We've loaded 2 packages here, and wherever you see ncdf4 : those functions are from the ncdf4 package, and wherever you see fields, that's coming from the fields package. So this is the function. We're going to open this netcdf file. So ncopen is the function that we want. And all that ncopen requires, if I have any question about it, I'll come down here and throw open ncopen. ncopen requires a file name, and that is the only argument here that doesn't have an automatic filled in response to the argument. So in this case, we don't want to overwrite the file, so write is automatically set to false. Read unlimited equals to true. All of this stuff don't worry about. In special cases, when you get more advanced, you might want to play with these, but for now, these arguments that already are predefined we don't have to worry about. We don't even have to reference them here. So what this is my file name. Notice something here though. Whenever you see file names in a computer, and you're not only referencing the file name, this long, ugly name of the file, but you're also going to need to tell R in which folder or which directory this file lives. In my case, it lives in a path. This is my path. It lives in my documents, GitHub, Geog 473.603 datasets folder. For you, it might be different because you just downloaded everything. It might be in your downloads folder, and you might have to unzip that package that we just downloaded right here and go through that. But if you're ever confused about the path, remember, tab is your best friend. So let me remove this and let's find where this is. So whenever you pop open quotation marks like this, RStudio automatically puts the beginning and the end for you because you always need an open and a close. So I'm going to put my cursor right in between these 2 quotation marks. I'm going to hit tab. This is what is called the root folder that R is referencing. This is the base of where R is referencing. So I'm going to go over to, in my case, it's in Documents, GitHub, Geog 473.673, datasets, and now this is where all the datasets live. And for this case, we're going to be using this long, ugly name. So now we have our path and our file name, and notice the .nc extension. I can hit Command Enter or Control Enter if you have a Windows machine, and boom, that file ran. So I can print out what this file is. It gives me a lot of information. There's 4 variables inside of it. band 15, DQF, SST, projection. Ignore the warnings. It gives me a dimension size. We have only one time dimension, so this is only one snapshot of what the satellite is seeing, and we have a box of latitude and longitudes. Then we have some extra global attributes, and these are just metadata. It says who created this file. I did. It gives the institution. These are just random different little metadata pieces that could be really helpful. So all we are concerned about is the variable. Now, when you read in a variable, in this case, we want to read in SST. So I'm going to load this variable open, SSTK. And so I'll notice when I print this out, this is kind of ugly. It's kind of wonky. And why is that? It's just stored really oddly. It's a large matrix. And if we pop this open, your computer might freeze. Mine's a pretty good computer, and you can see that it's already spinning because this is a massive file. It's 42 megs. I mean, you're over 5 million data points here. So this can freeze your computer. So I do not recommend clicking view on this. So I actually need to force quit that and just pop back open. And this is a good example. So watch what happens when we reopen here. Okay. So that no longer exists, which is fine. But notice how all my code automatically saved. So in that case, this happens from time to time. I'm just going to rerun everything that I've run so far. And now instead of running a view or trying to click on this large matrix and open it, I'm just going to run a summary. Now notice that all of these V's pop up, and this is a much different summary than what we've received before. What we can do is we can convert this to a vector format. Whenever you see V's in here, whenever that prints out, that means that it's reading as a vector, and that each point is a vector. We need to vectorize this entire matrix. And remember, vectorize means that we're going to convert it from a large spatial matrix to a single long data-ridden array. So really just a one-dimensional array as opposed to two-dimensional. So we're not converting it to that, but we're saving it as that, but we're going to convert it temporarily using this, just so we can view a summary of the data. And we can take a look at this and we can see what the mean is. So the mean is 278 Kelvin. We see we have about 2 million NAs or not available. We see the max temperature is 310 Kelvin, and so on and so forth. But just as a reminder, because I didn't convert SSTK to be a vector as of itself, if I just were to run summary on SSTK, we'll get that vector thing again. Why does that happen? Because I did not save this. And you don't want to. So we're just going to pop that open, just run a summary. That's all we are going to do. So next thing that we're going to want to do is, even though SSTK has dimensions of 2778 by 1989, those dimensions are just the number of rows and the number of columns. In this case, what the type of data set that we're looking at is a spatial data set. So the rows and columns, instead of having a row number and a column number, they have latitude and longitude. So imagine that this is just a large Excel spreadsheet, and each cell within that Excel spreadsheet has a temperature value. And the row corresponds to the latitude, and the column corresponds to the longitude. So we need to read in these latitude and longitude variables, because even though they're dimensions, they don't have values yet. So we're going to load in both of these. And I forgot to comment up here, so let me throw that in. And Now we have a lat and a long. And so I can run summaries on these, and I can run a dimension on these, and notice that it's just has one dimension, and that's because it is a vector already. And we can see that we have minus 50 to minus 100 is our minimum longitude, and for latitudes, our minimum is 16 degrees north, and our maximum is 52 degrees north. So those are read in, and even though we don't have them right now, we don't have a use for them at this moment, we will use them in the future, and you'll see how. The next thing that we want to do is we want to convert the SST from Kelvin to Celsius. It's a little bit more intuitive to work with this in Celsius. So what I'm going to do here is I'm going to subtract 273.15 from every value within SSTK. Remember, we have over 5 million points. Watch how quickly this is run. Done. So now, SSTC is the same size, the same dimensions. If I run a dim on SSTC and I run a dim on SSTK, they're the same exact dimensions, but here is where there's a difference. If I run a summary as .vector, so we can vectorize this and really crunch the numbers quickly, versus SSTK, here's the difference. So all we did there was we just converted the values that are within these variables to Celsius, from Kelvin to Celsius. Now, one problem that we notice here, though, is that we have a number of NAs, but if we take a look at our minimum values, negative 999 is a complete unrealistic Kelvin value. For those of you who don't work with Kelvin often, it is universally impossible to have a negative Kelvin value. So what we're going to do is, we need to get rid of every single value below 0 for Kelvin. And furthermore, we're going to take one step closer. We're going to make every value below 0 Celsius equal to Na, not a number or not available. Why are we doing this? Because if the sea surface temperature was 0 degrees, it would be frozen. So in our SSTC vector, all of these values, anything that is below 0 is unrealistic. It's not a real value. So what we're going to do here is we are just going to say SSTC bracket, and this bracket can be read as where. So we have SSTC where SSTC is less than 0 equals Na. So watch what happens when we do this here. I'm going to retype summary as vector of SSTC before and after this. So now we converted every value below 0 to Na. Pop open the summary again. Look at the difference here in NAs. We added about 500,000 Na values, and we also look at our new minimum here, 0. So that's really what we're looking for. That's what we want. Now that our data is ready to go, we did some data manipulation, we need to plot it. And in order to plot this, a great way to plot spatial data sets is the fields package. Fields package has a function image.plot. And if we actually go ahead and we do a question mark on image.plot, or the same thing as help, we see, okay, these are the different arguments that it takes, and these are the explanation of the arguments and what you can have here. And you use this function more and more, you kind of get used to how it works. And so we take a look down here at the examples, and we see that there's an x, y, and a z in this image.plot function. And in our case, our x is going to be equal to our ln. So just a reminder, ln is just our longitude values. Our y is going to be equal to our latitude values. Our z, or what fills in this domain, is going to be our Celsius sea surface temperature values. And then we can add in a legend.lab right here. This argument is equal to Celsius. So we're going to plot that. It might take a couple seconds. This is a pretty big file and has a pretty high resolution. So, and real quick, will say another thing about the GOES SST is that we can get down to 2 kilometer resolution. So pretty fine resolution. So notice that the stop sign went away here. We're back to a sideways caret and a blinking cursor. That's good. That means that everything finished running. Now you'll notice that we're still waiting in our plot window here. Nothing has popped up in here yet. So what this means is that, we might need to wait a couple seconds more before it actually pops up. There it is. Here's the image. Why did it take a couple seconds to pop up? Because we have 5 million points that it's trying to color here. So again, this is a massive spatial data set. And there are faster ways to go about plotting this, but this happens from time to time. Just remember that whenever you have a sideways caret and a blinking cursor here, you have successfully ran that code. So we go back over here. This is our plot. It looks good, and this is like an exact kind of representation. We expect that down here, this is here's Cuba, here's the Yucatan Peninsula, Mexico, here's Florida, here's the eastern seaboard, and here's Newark right here. So it kind of makes sense. We expect that temperatures down here in the lower latitude waters closer to the equator receive more sun. They'll be hotter as a result, and the water up here, up by Newfoundland and Canada, will be cooler. So there it is. The only other thing we're going to add here is a title. So notice how if I just run title quickly like that, it doesn't know that I want to add the title to this specific plot. So I'm going to rerun these together. Now, if I run them together, again, we're going to have to wait a little bit because this takes a couple seconds to actually plot and load. But what you'll see is that because I ran these together, it automatically associates that I wanted this title to be associated with this plot. So here we go. There's the title right there. So there it is. This is a pretty big, it's a pretty high resolution image, and it takes a couple seconds, and there are faster ways to go about plotting this for sure. And we will be covering those packages as well, but this is a really nice, easy, user-friendly package that I wanted to get started with because it makes a little bit of sense. Okay, we have our X, which is our longitude values, we have our Y, which is our latitude values, and we have our Z, which is just we fill in these boxes that we've set. And so just remember that this data is 5.5 million points. So this is a pretty massive data set, and that's just why it took a little bit longer. So ran through that, and again, everything that I just did over here is described in more in depth in a tutorial. So if you're a more visual learner, somebody who likes to read and follow along step by step via reading, I have all of that right here. So now that we're done with that, I'm going to go ahead and just save this file. So we're going to go to File, Save As, go to the folder that I want, and just type in whatever you want. Just remember that we do not like spaces in file names. It's bad practice. I would just do SST_example.r, choose my folder, save it, and now I can load this back in anytime. So that concludes this quick example tutorial, and now what I'd like you to do is to, with that same data set, make a plot of the DQF, the data quality flag variable. So we want to try and make this image with the data quality flag, and what this variable is, it tells us which pixel points or which grid cell points are good, maybe good, or bad, or definitely bad. So in this case, what you're seeing here is a considerable amount of clouds. So wherever we have clouds in the way, we are not actually able to get a great reading on the sea surface temperature. So we notice these white spots right here, and these white spots are NA values, not available values. So it makes sense. We're looking at sea surface temperature. We don't have any sea surface temperatures over the land, and then we also don't have any sea surface temperatures on places like this, which are just, we don't have sea surface temperatures there because there are clouds in the way. So the values for these are the kind of values that we got rid of using this step right here, where we said, hey, if the sea surface temperature value is below 0, I want to convert all those to not available. And that's what we did. Otherwise, these temperatures would be like negative 900, which is impossible. So basically what I'm saying here in maybe a little bit more detail is that what you're seeing is where you see these blue values, that's a DQF of 0, and that means that is good, high quality data. Where it is 3, it's definitely not good data, so notice how it's all land right here, so we know that we should not have any sea surface temperature values from there. And where it's this orange yellowish color right here, that is a data quality flag of 2, and that it means that there's clouds there, most likely. So go ahead and try and make this image and reference this tutorial, and I've given you all the tools that you need to make that image. The last thing that I just wanted to cover real quick is data types, and really it's just a little bit of indexing and dimension figuring out. So we've run the dimension here, and so we can tell, and we can run the dimension on the lat. If we run dimension on SSTC, we notice that it's 2778 by 1989, and we notice that the lat is 1989. So what that means is the dimensions of SSTC is long by lat. Lat 0 is a numeric, so we can actually run this over here. Lat 0 is a numeric of 0, and I remember we can also index this or subset it or slice this. You'll hear this called multiple different ways. So he's noticed that the lat of 0 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is like so. So a lat of the first value of latitude is going to be this value. Why is this? Because R is 1 indexed. What I mean by that is your first index is 1, it is not 0. For those of you who will be taking Python to me, will notice you will have some headaches because Python is 0 indexed, going from 0 to 10. In this case, a lat of 0 to 10 is skipping the 0 value because it doesn't know what that means. Why? Because it's 1 indexed. So a lat of 1 to 10 looks like that. Boom. So we can also go to the end there. So lat of 1989 has that value, and we can run a tail on lat, and notice that our length of lat is 1989. We plug in the 1989 value, 51.98563, and then we print a tail, last couple values of lat, in this case last 6, 51.98563. So just to get a glimpse on just a little bit more practice with some hands-on data that might be worth getting into, just exploring dimensions, slicing, subsetting, indexing with an array that is lat. This array, because it's one dimension, is also a vector. And yeah, that concludes the rest of this tutorial and this video lecture. So in-class exercise, make this plot.